Okay, so just a quick example here. This is really one of the ones that everyone assumes is so obvious that nobody actually ever tries to prove, but you can prove it. So two resistors in series, in other words one after the other, so R total is just simply R1 plus R2. It'll become kind of obvious why we want a proof a bit later when we do some more complicated examples. But if I put two resistors like this, one after the other, here's my voltage source and I've got a closed circuit, does the total resistance, let's write that down, let's formalize that, so does R total, I'll just call it R tot, equal R1 plus R2? Well, you'd have to be a brave person to try and say that that wasn't true, but there's a lot of people out there who say, well, you can't actually say things without proving them, so let's see if we can prove that, shall we? So from this voltage we must have a current flowing, and let's call that current I, and I think we all know from Ohm's law that that current will flow through R1 and R2 and all the way around the circuit. It's the same current, Mr. Coulomb and all that. So what we have an associated volt drop. So we're going to have a volt drop across R1 because of the current flowing through it, and we're going to have a volt drop across R2 because of the current flowing through it. So I'm going to call that VD1 for volt drop 1, and that's going to be equal to the current times R1. And we're going to have a corresponding volt drop across here, which we're going to call volt drop 2, and that's going to be I times R2. Nothing earth-shattering there really at the moment. Now, Kirchhoff's voltage law tells us that in a closed circuit, the voltages around a closed loop will sum to zero. That'll become more obvious with what I say in a minute. So in other words, this V here is equal to, sorry, done that wrong. We said that around a closed loop the voltage is sum to zero, so therefore V, this voltage here, minus VD1 minus VD2 is equal to zero. That's a funny way of looking at things, very odd way of looking at things, but actually if we arrange that it's not so funny at all, because what we have is what I started to write here, but mistakenly. So I have V equals VD1 plus VD2. Now that's obvious, isn't it? Because you've got a voltage here, what's dropped across here plus what's dropped across here must equal this one. Alright, we're no nearer though solving what we set out to do, are we? Which is to show that two resistors connected one after the other in series, the resistance total is equal to R1 plus R2. So how are we going to do something about that? Well, actually with mathematics always what you're using is substitutions. So VD1, we actually have a substitution for VD1, which is this here. Colours don't come out very well on this camera, but I'll try drawing around that in red. So VD1 is that, and VD2 is that. So let's just try writing that down in that form. So I end up with V is equal to I, because there's only one current flowing in the circuit, times R1 plus I times R2. Okay, that's where I got that from, those two up there. Okay, now it's starting to become fairly obvious what I think we're going to try and do now, which is that let's just take the I's out. This is painful maths, but we'll do it for the people who are not comfortable with maths. So V equals I times R1 plus R2. We saw that in another example. So how does that get us any closer to what we want? Well, actually, here's the magic. Now if I take the I here and put it on the other side, V upon I is equal to R1 plus R2, but we have to ask ourselves the question now, what is V upon I? Well, V upon I is bound to give the total resistance, right? So V upon I is equal to R total, and we just showed that R total is equal to R1 plus R2, so there we have it. A whole load of maths to prove what you already knew anyway, but that's where it came from. Rather nice. See you soon.